Hello, my name is Natalie. I'll be presenting with Adam, and we'll be talking about weak lensing investigating dark matter distribution in galaxy clusters. Thank you to Professor Kallan for inviting us both to talk today and to share about our research that we did together last year. We're very excited to present, and we did this research in collaboration with Northeastern University. Okay, so first we're just going to talk about the background and then some data collection methods that Northeastern did before we joined the project, and then Adam's going to dive into the Python pipeline and some results as well. Okay, so first is the question, why do we even want to study dark matter? Why do we care about what it is? Well, visible matter only makes up about 5% of the universe, which is very, very tiny. If all that we can see and detect with our telescopes is just 5% of what is actually out there, it means everything else, dark energy and dark matter, are really worth studying. And dark matter makes about 27% of the universe. So we really don't know much about it, and we really want to know more. Okay, so when we ask what is dark matter, since I already mentioned that we cannot observe it, we cannot detect it directly, we can only observe the impact that it has on baryonic matter, which is just regular matter that we can see and interact with and detect. So examples of this is anything that we detect in the visible spectrum, but also ultraviolet, X-rays, stuff like that. That's all baryonic matter. Dark matter does not fit into that category because it is completely indetectable with our technology. And the biggest interaction that we see, how dark matter interacts with baryonic matter, is via gravity. That's mostly how we know that something is there and it exists, and we call that something dark matter because of the gravitational pull that is unexplained on baryonic matter. And dark matter explains that gravitational pull. So just to talk more about gravity and space-time in general, just as a review, not sure if you already covered this in your astrophysics class, but if we imagine the fabric of space-time to be like a sheet, and if we imagine like a big star, such as the sun, like a ball on that sheet making a little dent, and our planets going around it, that is like the gravitational pull that the sun has on our Earth, demonstrated by the curvature of space-time. When we look at something like a black hole, just for a really extreme example, a black hole has a very extreme curvature of space-time. So we can see that there's a dip and it just goes straight down, and that's just a very extreme example that I wanted to show to illustrate the point. But for the purposes of our project and weak lensing, we looked at galaxy clusters as our lensing object. So to just explain what lensing even is, it's basically when an observer, so if we start down here, looks at a distant star and say there's a massive object in the way. The light from that star gets bent by the curvature of space-time, because light will always take the path of least resistance, the path that is shortest to travel. And if that path is bent, then so will the light be. So when we are here at the bottom, and when we see the light beam coming towards us, toward Earth, and we trace it back, it appears that the star is coming from a different point than it actually is physically located in. And this is because the phenomenon known as gravitational lensing. Yeah, so for our project, we used galaxy clusters as our lensing object. So a lot of galaxies all clustered together, and we looked at it, and we looked at the light behind it and saw how much it got lensed to kind of gauge how strong is the gravitational pull of these galaxy clusters. Now I will mention just quickly, because I don't think I said this, but yeah, for these galaxy clusters, we see that when we examine the mass of each individual galaxy, we see that they are not massive enough to continue to be a cluster. Because of the expansion of the universe, they should be moving away from each other and not staying in this cluster. So that's how we know that dark matter is present, is because there's extra matter adding to the gravitational pull that is indetectable. Okay, so when we looked at, this is just an example, but when we looked at like lensing, this is how light gets bent. So everything, all these lines in red kind of represent the shear, which is kind of like the stretching and bending of light. Yeah, so you can see how the shear is affecting all these objects that are being lensed. They're all kind of in this circle around this object that is lensing them. And so by examining how much or how little the object is distorted, essentially, it's how we know how big the gravitational pull is. Okay, so now that we dove into a little bit of the background about weak lensing and dark matter, we can actually go into data collection, which was the first part of this project that Northeastern University did. Yeah, and it's pretty exciting. So the way that they actually got all the images and data that we interpreted was by putting a telescope up in the stratosphere. And they did this with a balloon, if you believe it or not. It's called SuperBit, also known as Super Pressure Balloon-Borne Imaging Telescope. So up here, we see that there is this big white balloon. It's kind of funny, but it's a balloon. And its main drawback is that it's very thin, and it is resistant to, obviously, to wind and stuff, but unfortunately there have been cases where the balloon pops and the telescope drops down. But yeah, so there's the balloon, and there at the very, very bottom, that's the telescope. And this basically floats in the stratosphere, which is above 99% of the Earth's atmosphere. And this lets it get up above the Earth's atmosphere, so it doesn't have that in the way of all the images and data it's collecting. But it also means that it's not going all the way up to space, completely away from Earth. So this makes it rather an affordable way to collect data, because it's still in the atmosphere within Earth's orbit and all that. Yeah. When we talked to the Northeastern University students, they said it was actually it's about $5 million, which is, believe it or not, cheap for this kind of thing. So it's often used by certain universities and research projects for data collection. And this is just an example of an image taken by SuperBit. And this is of the sun, and this is the Earth. Yeah, so this is what the image would look like. So obviously some of Earth is still in there. And Adam will mention this more, but when SuperBit took the images, it would take about 5-minute exposures, and it would do about 30 of those exposures per galaxy cluster, roughly. And then some of the pipeline had to stack all these exposures so that we would get an accurate image, and then a lot of it was cropping out where the Earth was, stuff like that. Yeah, Adam will talk more about that part. I just wanted to mention it. Yeah. So now we're onto the Python pipeline. I'll hand it over to Adam.
Hello everyone, I'm Adam. Nice to meet you all. I worked with Professor Kallan and Natalie last year on this research, and I still work in this research today with Northeastern. I'm planning on doing it for my undergraduate thesis next year, and I really love this stuff. So my job today is to talk to you guys about the pipeline and the future directions of the field, right? But first, I want to kind of take a step back and talk more generally about astrophysics. We remember what Natalie was saying about the lensing and shear. So I want to talk about the idea of an inverse and a forward model into astrophysics. So lensing, and in weak lensing, we have something called the weak lensing equation. And basically it tells us, given where the mass is in the sky, how the light will be lensed, right? So it looks like this. Right? In this case, kappa, or K, is the mass map, and psi is the lensing potential, right? What does the lensing potential mean? Well, if we remember what Natalie said about shear, basically shear is given by the second order derivatives of the lensing potential. So this is what we call a forward model. We, given some mass, can get out how light will be affected. But let's stop and think about what we have in real life. Natalie kind of already talked about it, but basically what we have are pictures of galaxies. I'll put a picture here of a large field of multiple galaxies. And all we can do is look and see their shape, and that is the shear. So we have to go from the second order derivatives of psi back to the mass map, which is ultimately what the scientific goal is to see where mass is located in the sky that we just took a picture of. So that is an inverse problem. In astrophysics, this is a very common pattern that you'll see. If you ever want to do research or look more into the field, almost all of astrophysics are inverse problems because we have lots of data that is noisy and we're trying to figure out what caused it to be the way it is, right? So now that we understand what an inverse problem is, we understand what our pipeline is trying to do. Ultimately, the pipeline is trying to be an answer to the inverse problem of this equation systematically for the images that we take with our telescope. Okay, so we understand what an inverse problem is. Let's start at the very beginning, the images that SuperBit takes. Okay, so SuperBit takes multiple short exposures of the same patch of sky, 30 of them, 5 seconds each. Then we save them as FITS files. FITS files are basically specialized files that save metadata of the telescope, such as the angle that it's pointed at and exactly where it's pointed at in the sky, and we use that information to do a process called co-addition. The idea is that every single 5-second exposure is blurry, but we want to reduce that blur by adding up multiple, we took 30 pictures of the same patch of sky. And so the process is called co-addition, and what happens is roughly with the square root of the amount of exposures, we reduce the noise and get a much deeper image out. I want to show you what this image looks like. It should be on the screen right here, because I think it's really important. So this is the image that we actually do our science on. Each one of those points is a galaxy, and each one of those galaxies is a potential shear measurement. From that coad, the next step is source detection. We use a software called Source Extractor, which basically looks for connected regions that exceed some signal-to-noise ratio above the local background. So then we get out these blobs. Each one gets an entry in a catalog and a location in the sky, and then a general shape. I'm going to show a picture of these stamps on the screen right now. Our first complication is deblending. Basically, galaxies often overlap in projection, and so we have to decide whether or not we're seeing one object or two objects. Source Extractor has a deblending algorithm that tries to separate them based off of local flux topologies, but it's an imperfect process. Without this deblending step, later on, our shape measurer would be measuring the shape of two galaxies that have been kind of melded together, contaminating our results. It's estimated that entire percentages of error could come from this step alone, making it a good active landscape for research by students like you and me. Before we move on, let's check in with each other. What we've done so far is taken in a coad image, which I'll put here, and then we ran a software called Source Extractor that outputs stamps of galaxies, which I'll put here. There's hundreds of thousands of these stamps, and basically the next step would be to measure the shape. But before we do that, crucially, we have to correct for the PSF, the point spread function. Any optical system, including SuperBit, blurs and distorts the image it takes, and that blurring varies across the field of view. An imperfect analogy is an astigmatism, where people will see a point of light as spread out. Basically, the way we correct for this effect in astrophysics is we notice that stars that are really far away can be assumed to be point sources. And the way that they are spread out by the telescope away from point sources will be the PSF at that point in the sky. And so then we can find the PSF at every point in the sky and then correct for it in our galaxy pictures. This is called deconvolution, and we do it to every galaxy. Without this step, our shape measurer would just be measuring the shape of the PSF and not of the actual galaxy. Okay, so checking in again, we now have that exact same galaxy stamp, but it's a little less blurry this time. And I'll put a picture of SuperBit's PSF on the screen here. This is what we took out of the image. And then this is what the image looks like now. Not too different, but it's really important. With the PSF removed, we now move to the heart of the pipeline called shape measurement. This is often done by a package called ngMix. ngMix fits a model, typically a Gaussian distribution, to each galaxy's light profile and extracts ellipticity components. But there's one key issue. Basically, every galaxy has an intrinsic shape and a shear shape. And so we can't really distinguish between what is intrinsic shape and what is shear shape. But what we can do is average across many, many galaxies, assuming that the intrinsic shape will be randomly aligned, and then average out to 0. And what's left is a spatially correlated shear signal across many, many galaxies. This leaves us with only shear, the measurement we were looking for. The catch is that ngMix, like any shape estimator, and estimator for that fact, has bias. It doesn't return the true shear, it returns something systematically offset from it. This is where meta-calibration comes in, and it's kind of an elegant tool. The basic idea is that we take images, we artificially shear them by a small, known amount, run the estimator again, and measure how it responds. This gives us a response matrix that tells us how sensitive our estimator is. Essentially, for every unit of true shear, how much does ngMix actually report? Importantly, the response matrix isn't encoding any physics. It's purely a property of the estimator itself. It works because, on average, real galaxies have no preferred orientation. If we assume that the average galaxy is circular, then any average ellipticity we measure must be coming from the shear, and the response matrix lets us convert our bias estimates into unbiased ones. Now let's do another check-in, right? We started at this coad, we got out stamps, we deconvolved the PSF, got out new stamps, and then we have now a catalog of calibrated shear measurements at positions scattered across the field. And we want to reconstruct the mass distribution that caused them. This is the inversion step, and it's kind of where the math gets interesting. Okay, so the relationship between kappa, the convergence, which I talked about earlier, and the shear that we just got out, gamma, is non-local. In real space, it's a convolution, but in Fourier space, it simplifies enormously. If you take the Fourier transform of the shear field, the convergence at each Fourier mode is just a simple algebraic function of the shear at that mode. One thing this naturally produces is two independent maps. The E-mode map captures curl-free distortion, which is what gravity produces. The B-mode map captures divergence-free distortion, which is gravity cannot produce at leading orders. So the B-mode is basically a test. If your B-mode is large, something's wrong. Either PSF contamination is still in your data, or some other systematic is still here. Here I'll show both. The E-mode on the left shows a clear peak, which is the mass concentration from the galaxy cluster. The B-mode on the right is much flatter and noisier, which is roughly what we'd hope to see. It tells us that our systematics are roughly under control. From the convergence map, we also compute the tangential shear profile around the cluster center, which should fall off with a radius in a way that matches an NFW profile. We fit that to recover the cluster mass. So now let's talk about active research in the field. I get to talk about my own research, which I'm kind of excited about. The first thing I want to mention is ShearNet. It works to replace ngMix as the shear estimator in our pipeline. And basically, the advantages of this is that it's a neural network. And the neural network should be a lot faster and possibly even more flexible to things like PSF. The second thing I want to talk about is FEMI, finite element mass map inversion, which aptly named fits right in the section where we want to invert from shear to mass maps. The basic idea is to use finite element method to solve the forward model, the PDE that I wrote on the board earlier. Then we take a guess at the mass map that's contributing to the shear field that we input to FEMI. So we take a random guess, we solve the forward model, we get the shear field out, we compare it to the shear field that we inputted to FEMI, and then we iterate over and over again until the shear field that's outputted by FEMI's guess matches the inputted shear field from the shape measurer. And then the third thing I want to talk to you about is what I hope to be my undergraduate thesis here at WPI. This will take place next year, and I'm hoping to make two more products. A neural network-based source extractor and deblender, which should do it all in one step, and then a PSF deconvolution neural network. The PSF deconvolution neural network is actually kind of already made. I just haven't benchmarked it. And And then stringing all these together, I think you might notice, it makes an entire pipeline. So I'm hoping by the time my undergraduate degree is done, I might have made an entire pipeline that goes from coaddition images to mass map images. So now I hope you have a good grasp on the field of weak lensing, and if you have any questions, don't hesitate to reach out to me or Natalie. Thank you, Professor Kallan, for letting us speak today. I hope you guys liked it, and bye.